Thank you for watching my videos all these years and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solutions of previous year questions from the section analysis that have appeared in the CSIR National Eligibility Test. In this video, we discuss 4 questions, question number 8 to 11. All these questions are suitable for these examinations. Right. This question has appeared in 2016 June for a multiple select question for 4.75 marks. The question is related to countable and uncountable sets. The given question is, let A be any set. Let P of A be the power set of A, that is, the set of all subsets of A, that is, P of A is the set of all B, such that B contained in A. Then, which of the following is or true about the power set of A? We are given 4 options. Option 1, power set of A is empty for some A. Option 2, power set of A is a finite set for some A. Option 3, power set of A is a countable set for some A. Option 4, power set of A is an uncountable set for some A. Let's now discuss the solution of the problem in detail. We are given capital A, any set. We have power set of A denoted by P of A is equal to the set of all sets B such that B contained in A. It is the set of all subsets of A. Right. Now, we take option 1. Can the power set of A be empty for some A? Is it? Note that order of power set of A, what is the order? 2 power order of A, right? It's well known. Assume that power set of A is empty for some A will imply taking the orders on both sides. Order of P of A is equal to order of phi for some A. Order of phi is 0. This implies and order of power set of A is 2 power order of A is equal to order of phi is 0. And what will be the order of A? The minimum order for A is 0 when A is empty. So, 2 power order of A cannot be equal to 0 because order of A can be non-negative integer, and 2 power order of A is 0, and this is not true for any set A including the empty set. So this is a contradiction. So contradiction says your assumption that power set of A is empty for some A is not true. That is, power set of A is not empty for any set A. Therefore, the option 1 is not true. Right. We move on to the next slide for the discussion of the remaining options. Right. We take option 2 and option 3. Option 2 says power set of A is finite set for some A. Is it so? Power set of A is countable set for some A. Is it so? And both are true. Now how? Let A be any finite set. Then order of power set of A is 2 power order of A. Order of A is finite. Because A is finite, therefore order of A is finite. 2 power order of A is finite. Therefore, why it is finite? 2 power order of A is finite. Why? Because A is a finite set. So, power set of A is a finite set for any finite set A. Therefore, option 2 is true. And from this, option 3 is also true. Why? For any finite set A, power set of A is finite and every finite set is countable. Therefore, power set of A is countable set for any finite set A. Therefore, for some A, this is true. So, that is the option 2 is true. From that, option 3 is true. Further, power set of A is a countable set because it is a finite set for any finite set A. Therefore, option 3 is also true. So, power set of A is a countable set for some finite, for any finite set A. Therefore, option 3 is also true. Option 4. Power set of A is uncountable set for some A. Yes. Let us take A to be set of natural numbers. Then order of power set of A is equal to order of power set of n is equal to 2 power order of n. What is order of n? N is countable. Therefore, its order, its cardinality is LF naught. So, 2 power LF naught. 2 power LF naught is C. C is continuum and it is uncountable. So, that will tell you power set of A is uncountable set for A is equal to n. And you can argue for any countable set A, this is true. Like countable sets like n, z, q. N means set of natural numbers, z means set of integers, q means set of rational numbers. They are all countable. Therefore, your argument is valid if you take A is n or z or q. So, thus option 4 is true. So, the answer to this question is options 2, 3 and 4. That is the detailed discussion of the solution of the given problem. Right. We move on to the next slide for the next question. Right. This question has appeared in 2015 December examination for 3 marks. It is the question is based on the concepts of open and closed sets. Right. The given question is, let A be a closed subset of R and A is not empty and A is not whole of R, a set of real numbers, then A is. We are given 4 options. Option 1, the closure of the interior of A. That means then A is. Can A be the closure of the interior of A? Can A be a countable set? Option 2. Option 3, a compact set. Option 4, not open. Let's now discuss the solution of the problem in detail. We have capital A given to be a closed subset of R. It is further given A is not empty and A is not the whole of R. So what is A? A is a closed subset and A is not empty and A is not R. Such a you have to take. Right. We go to the option 4. Option 4 says not open. Is it true? Yes, it is true. Now assume A is open. That means we give the proof by contradiction. Assume that A is open. But A is open, but A is the common hypothesis. A is closed also. Therefore, A is both open and closed. Open by your assumption, closed since it is given. So A is both open and closed. Now, in R, who are the subsets of R which are both open and closed? It is phi and the whole of R only. A is equal to phi or A is equal to R, since phi and R are the only subsets of R which are both open and closed. But it is a contradiction. Why? In the common hypothesis, how A is to be taken? A is not empty and A is not R. And when you assume that A is open, then you get A is empty or A is R. A contradiction. Thus we arrive at a contradiction. Therefore, our assumption is not true. Your assumption that A is open is not true. Therefore, A is not open. Thus, option 4 is true. Right. We move on to option 2. A countable set. That means when A is a closed subset of R and when A not equal to empty and A not equal to R, can A be a countable set? A closed subset of R, you take a closed subset of R, which is not empty, which is not R, is not necessarily countable. For example, A is a unit closed interval, is a closed set, which is not phi, which is not R, but this is uncountable. Therefore, A is a countable set is not true. Therefore, option 2 is not true. Option 3. When A is a closed subset of R, A not equal to phi, A not equal to R, can A be a compact set? Now for that, you take let A is a semi-closed interval, 0 to infinity. Now, A is equal to the semi-closed interval 0 to infinity is a closed set. Why? Because its complement, when you take its complement, the complement of the semi-closed interval 0 to infinity is the open interval minus infinity to 0, which is open. So, A complement is open means A is closed. Right. But now A is closed, A is not empty, A is not R. Now, can this A be compact? That's the question. So now, note that A, the semi-closed interval 0 to infinity is not compact because it is not bounded. On R, who are the compact sets? Closed and bounded sets are compact. This is not bounded, therefore it's not compact. Thus, option 2 is not true. We move to option 1. The closure of the interior of A. Can A be equal to the closure of the interior of A when A is a closed subset of R, when A not equal to phi, A not equal to R? For this, let A be any finite non-empty subset of R. Take any finite subset of R which is non-empty. Because it is a finite subset, it is closed. It is closed because there are no limit points and hence it contains all its limit points, therefore it's closed. Every finite set is closed. Why that? Now, the interior of A, because it is a finite set, we do not have the interior points of that. and the interior of a finite set is empty, and if you take the closure of the interior of A, that will be the closure of phi. The closure of phi is phi only and not equal to A, because A is not empty. A is a finite non-empty subset. A is not. It is not equal to A. Thus, option 1 is not true. Good. So, the answer to this question is option 4. That is the detailed discussion of the solution of a given problem from analysis which is related to the concepts of open and closed sets on R. We move on to the next question. Right. This is the question that has appeared in 2013 June for 3 marks. It is related to concepts of continuous function. Right. The given question is, in which of the following cases there is no continuous function, stress, no continuous function f from the set S onto the set T, stress onto. No continuous function f from the set S onto the set T. We are given 4 options. Option 1, S is the unit closed interval, T is the whole of the real number line. Option 2, S is the unit open interval and T is the whole of R. Option 3, S is the open unit interval and T is also open unit interval. 4, S is equal to R and T is the open unit interval. What is that you have to find out? You have to find out those cases where there is no continuous function f from S on to the set T. S and T's are given here. Let's now discuss the solution of the problem in detail. Right. Take the first case. Option 1. S is unit closed interval. T is the whole of R. Now, if you are familiar with continuous functions or non-continuous functions, and I'm sure from your intermediate, that is from the +2 level from calculus, you can think of a good example like this. Right. Note that S is 0 to 1 is compact. Right. T is R is not compact. Correct. So, assume that there exists a continuous map F from S unit closed interval onto T is equal to R. Now, f of S is R because it is an onto function. Now, note that f of S is compact. Why? Because f is continuous, and S is being a closed unit interval, it is compact. F of S is compact since the continuous image of a compact set is compact. But what is f of S? R. So, this tells you R is compact, but it is a contradiction because R is not a compact set, right? So this contradiction tells you your assumption that there exists a continuous map F from S onto T. So there is no continuous. Therefore, there is no continuous function F from the set S onto the set T. So, you have to find out that case in which there is no continuous function. So, option 1 is true because you have to find out a no continuous function, right? Option 1 is true. And if you prove that there exists a continuous function, option is not true, right? We move on to option 1. and it is being a 3 marks question from section B, only one answer is true. Therefore, that answer we have found out, and therefore you need not worry about the other remaining options. And the answer to this question is option 1. But however, our students will ask, how do we show the other options are not true? Okay, we will go for that. Option 2. S is unit open interval, T is whole of R. Yes, it is here your knowledge of intermediate that works. Right. Define a map F from S, the unit open interval, to T is equal to R by F of x is equal to tan of pi x minus pi by 2. The domain is 0 to 1. The range is whole of R. It's the most familiar question from our intermediate, and this is the unit interval, and this is your tan function. And it says, it is well known that this map is bijective, 1, 1 and on 2, continuous, because it's a continuous map you got, and it maps the unit open interval onto T is equal to R. So there exists such a continuous function. Therefore, this option is not true. So you have to find out no continuous function. So there is a continuous function f from S onto T in this case. Therefore, option 2 is not true, because you have to find out that function which is not continuous. Let's move to the fourth option directly. The fourth option is S is R, T is equal to 0. That means the roles of S and T are interchanged. In the case of S to T, we have found out a bijective continuous map which maps S onto T. So take the inverse of it, because that function what we have discussed in option 2 is bijective. Therefore, its inverse exists and will be continuous, and it will map R onto the open interval 0 to 1. Yes. Therefore, there exists a continuous function f from S is equal to R onto T is equal to 0, 1, which is the inverse of the function that what we have discussed in option 2. The inverse of the function f of x, the above function, tan of pi x minus pi by 2 is continuous, and inverse of the function, why are we considering? Because that function was bijective. Every bijective function is invertible. So you have the inverse of the above function. The inverse of a continuous function is also continuous, and maps are onto the unit open interval. And for your ready reference, the inverse function is y is equal to 1 by pi tan inverse x plus 1 by 2. And option 4, therefore there exists a map, a continuous map, therefore option 4 is not true. We move on to option 3. S and T both are unit open intervals, and the answer, there exists a continuous map S onto T is very clear. You can take an identity map. Define a map f from S to T by f of x is equal to x. So it is 1, 1 and also, and it is bijective, and it is continuous, and it maps onto. So it is well known that this map, which is an identity map, is a continuous function and maps S, the unit open interval, onto T, the unit open interval. There exists a continuous map. Therefore, this option there is a continuous function f from S on to T. Therefore, option 3 is not true. So what is true? Only the option 1 is true. The answer to this question is option 1. And that is the detailed discussion of the solution of this problem. Right. We move on to the last question. This is the question that has appeared in 2015 December from the part C for 4.75 marks, and it is related again on continuous maps. Right. The given question is, which of the following statements is or true? We are given 4 options. Option 1, there exists a continuous map f from R to R such that f of R is equal to q. Option 2, there exists a continuous map f from R to R such that f of R is equal to z. Option 3, there exists a continuous map f from R to R square such that f of R is the set of all ordered pairs x comma y belongs to R square, satisfying x square plus y square is equal to 1, which is a unit circle. Option 4, there exists a continuous map f from the closed unit interval union the closed interval 2, 3 to the doubleton set consisting of 2 elements 0, 1. Right. So, let's now discuss the solution of the problem in detail. Option 1 says there exists a continuous map f from R to R such that f of R is equal to q. Can this be? Can this be? No. Why? If f is continuous from R to R and f of R is what? R is connected. F of R is given to be q. That means q must be connected. But it is not. Q is disconnected. Therefore, there is no continuous map. Assume that there exists a continuous map f from R to R such that f of R is equal to q. Since R is connected and the continuous image of a connected set is connected, you have to remember R is connected and the continuous image of a connected set is connected, f of R is connected. But f of R is given to be q. It means q is connected. It's a contradiction because q is disconnected. Therefore, your assumption that there exists a continuous map is not true. Therefore, there does not exist a continuous map f from R to R such that f of R is equal to q. Thus, option 1 is not true. In the same spirit, you can throw away option 2. Why? Because R is connected, f of R is z, and f is continuous image of a connected set is connected. That will give you z is connected, which is not true. Z is disconnected. The same argument is valid. Option 2. There exists a continuous map f from R to R such that f of R is equal to z. There does not exist a continuous map f from R to R such that f of R is equal to z. Since R is connected and z is disconnected, the argument same as in the option 1. Thus, option 2 is not true. We move on to the next slide for the remaining 2 options. Right. Option 3. There exists a continuous map f from R to R square, this time It's not from R to R, but this time R to R square, such that f of R is a set of all ordered pairs. F of R will be a subset of R square, set of all ordered pairs x comma y, belongs to R square, such that x square plus y square is equal to 1 is a unit circle. Right. Note that set of all ordered pairs x comma y belongs to R square, such that x square plus y square is equal to 1 represents a unit circle in R square. Yes. I can think of a function, define a map f from R to R square by f of t. T belongs to R. F of t will be an ordered pair, that is cos t sin t, where t belongs to R. Cos t sin t, as t varies on R, it will give you a circle. Now, it traces, f of t traces the unit circle as f of t winds around it periodically, many a times, but it will give you a circle. Now, f of t is an ordered pair consisting of two components, f1t, f2t. These two components, f1t cos t, f2t is sin t, they are continuous, and hence f is continuous. F is continuous because its component functions f1t, f2t are continuous. This is well known. You might have studied this concept in the functions of two variables. Thus, there exists a continuous map f from R to R square, such that f of R is set of all ordered pairs x comma y belongs to R square, such that x square plus y square is equal to 1. There exists. So option 3 is true. Right. We move on to the last option. Option 4. There exists a continuous map from f closed unit interval union closed interval 2 to 3 to the doubleton set consisting of two elements 0, 1. Right. Now define the map f from the unit open interval 0 to 1 union the closed interval 2 to 3 to doubleton set consisting of two elements 0, 1 by f of x is equal to 0 when x belongs to the closed interval 0 to 1 and f of x is equal to 1 if x belongs to the closed interval 2 to 3. It's very clear. F of x is continuous on the interval 0 to 1 and f of x is also continuous on the interval 2 to 3. But here it is given to be the union. Is it continuous on this union? F is continuous on the first set, union on the second set. Is it continuous on the union? Yes, provided the left limit of one of the function is 0 and the right limit of the function of 2 is 1. Then continuity you can think of. Now f of x is continuous on the first interval, closed interval 0 to 1, as it is a constant function. Right, every constant function is continuous. So also f of x is continuous on the closed interval 2 to 3 as it is a constant function. Now limit extends to 1 minus, that is the left limit of 1 of f of x. The left limit of f at 1 is 0, which is given to be f of 1. So it comes out some value, that value is equal to the value of f at 1. So also in the second case, limit extends to 2 plus, that is the right limit of f at 2 of x is 1, which tallies with f of 2. Thus continuity is achieved everywhere. Everywhere. Thus, f from this union to the doubleton set consisting of two elements 0 to 1 is a continuous map. It is a continuous map. Therefore, the option 4 is true. Right. The answer to this question is options 3 and 4. In the first slide, two options what we have shown to be not true. The answer to this question is options 3 and 4. That is the detailed discussion of this question from analysis related to continuous maps. And in this video, I have proposed 4 questions that have appeared in various examinations of National Eligibility Test and discussed them in detail. And they are all looking to be simple. I am sure that you have understood the solutions of these problems, 4 problems. Thank you for watching this video. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.